For linear functions whose graphs are not horizontal, the domain and range are all real numbers. However, in many real-world situations, the domain and range must be restricted. For example, some quantities cannot be negative, such as time. You can't have negative time, so that means that time always has to be positive. Sometimes domain and range are restricted even further to a set of points. For example, a quantity such as a number of people can only be whole numbers. When this happens, and remember whole numbers, that's just 0, 1, 2, 3. So no fractions, no decimals, no negative numbers. That's what whole numbers are. So for example, a quantity such as the number of people can only be whole numbers. You can only have like 1, 2 people. You can't have 2.5 people, all right? So only whole numbers. When this happens, the graph is not actually connected because every point on the line is not a solution. However, you may see these graphs shown connected to indicate that the linear pattern or trend continues. So you remember how we talked about discrete graphs and continuous graphs? And we said, hey, if you have distinct points, right, the domain and the range can only be on those distinct points. If this is my x-axis and this is my y-axis, right? And this was for a discrete graph. Now what this is saying is that if this pattern continues, then what you could see is that these lines are connected. And they're connected with this arrow to show that these points are going to continue. The trends are going to continue. Whereas the graphs that we looked at that were discrete, if they had points, we just looked at those individual points for the domain and the range, and that was it. Okay, so this is a different type. It says, hey, if we have a pattern, okay, so we're going to have a graph, and it's going to have those points, right, for the domain of value. This is what it can be, but this pattern is going to continue. So what we're going to do is we're actually going to connect the dots and put an arrow to show that the pattern continues. So when you see that there are distinct points, and they're connected, what that means is you're dealing with a discrete graph, but the discrete graph continues on and on forever. So that is the way that they show that mathematically. All right, perfect. Let's go ahead and look at a few examples here. So example 4, let's see if I can get this. Okay, got it all in the same shot. Great. It says an approximate relationship between human years and dog years is given by the function y equals 7x. Okay, where x is the number of human years. Graph this function and give its domain. So we're going to graph it. We're going to come up with some domain values. Notice here on the graph, the x is human years, so that means the x-axis is human years. The y's represent dog years. So whenever you're making a graph, you want to make sure that you label the x-axis, label the y-axis, and put a title on it. This is talking about human years versus dog years. So for human years, you couldn't have negative numbers, right? A human's never -1 years old, and dogs can't be negative either. So you know that we're only dealing with positive numbers for humans and dogs. So we're just going to be graphing within this quadrant 1. So let's just pick some values, 0, 1, and 2. And we have y equals 7x, but it's a function. That means it's the same thing. F of x equals 7x. So I'm going to find what f of 0 is, right? So I'm going to go 7 times 0, which is equal to 0. And then I'm going to go ahead and, this needs a column for the ordered pair, which would be x, and f of x, which is my y, right? So this is x, y, my ordered pair. So the first point is just 0, 0. Okay, let's go ahead and figure out what f of 1 is. So we stick 1 in for x. 7 times 1 is 7. So the ordered pair 1, 7. And then lastly, we're going to figure out what f of 2 is. So we have 7 times 2 equals 14. That gives us the ordered pair, 2, 14. Now we just go ahead and plot all these values. So our first is 0, 0 right here. Our next is 1, 7. So I got to look at these and see how 1, 2, 3, 4, 5, 6. Okay, so they're just in 1. So 6, 7 would be here. So 1, 7 would be here. 214, so 214, there's 15. One before it would be right there. So, and it looks like this trend is going to continue, right? So 3 times, 7 would end up being 21. And so we're just going to go ahead, and you can have human years. You can be like 1.5 years old, or, you can have fractions or decimals. So I'm actually this is going to be a connected line. Here. And it really shows that this pattern can continue on and on forever. So we graphed it, we filled out the table, we just need to state what the domain and the range is of this function. So the domain, or what are the x values? Well, we start here for human years, and it really goes on and on forever. I know that humans don't live forever, but this arrow distinguishes that it's going to keep going on forever. So for this, we're going to say that the, oops, sorry about that, actually bumped it. The domain is x is greater than or equal to 0. And then the range would be the y values, which again, we start at 0 and it goes on and on forever. So we would say y is greater than or equal to 0. So that would be the domain and the range of this particular application. All right, let's go ahead and look at the next one. Okay, so what this says is, at a salon, Sue can rent a station for $10 per day plus $3 per manicure. The amount she would pay each day is given by the function f of x equals 3x plus 10, right? So she has to give $10 per day plus $3 for every manicure she does. So x is probably going to be the number of manicures. So we're going to graph this function and give its domain and range. So whenever you're graphing, you remember that the x is the number of manicures, right? So we're labeling that x-axis, and the y is the total amount of rent that she has to pay. So we're, and this is dealing with rental payment. So make sure you label those axes and put a title for your homework. Perfect. And then we're just going to go ahead and plug in some values. So I'm going to say, okay, you can't have you can have negative manicures. So x has to be 0, 1, 2, 3, 4, 5, right? And you can't have like 1.5 manicures. I mean, they're really just going to be whole numbers. So let's go ahead and plug in these values and see what we end up with. So the first one is f of 0, which equals 3 times 0 plus 10. 3 times 0 is just 0 plus 10 is going to be 10. So we end up with the ordered pair. This is going to be x f of x. So that's 0, 10. Make sure on your ordered pairs you always put parentheses, okay? Let's go ahead and find the next one. F of 1 is 3 times 1 plus 10, which is going to be 3 plus 10, which is 13. So that means we have 113. Let's do the next one. F of 2 equals 3 times 2 plus 10. 3 times 2 is 6 plus 10 equals 16. So we have 216. And then f of 3 equals 3 times 3 plus 10. 3 times 3 is 9 plus 10, which is 19. So we have 319. And what else do we have? Right here, f of 4. We're going to figure out what. So 3 times 4 plus 10 equals 3 times 4 is 12 plus 10. That's going to give us what? 22. So 422. And lastly, f of 5 equals 3 times 5 plus 10. 3 times 5 is 15, which is 25. We end up with 525. Okay, now it's time to graph. So what do we have? 0, 10, that's our first one. Then 113 is right here. 216 is right here. 319 would be right here. 422, it's really faded. It's right there. 525 would be all the way at the top, I think right about, is that right? Yeah, right about there. Okay. So with this one, we cannot have, like if you have one manicure, the rental payment's going to be $13. If you have 2 manicures, the rental payment's going to be $16. If you don't do any manicures, you're still going to have to pay $10 for that day. So this is the rental payment. Is it per day? Per day, yeah, per day. And so you're not going to have 2.5 manicures and then pay this amount, right? You're only going to have manicures that are 2, 3, 4, 5, 6, and so on. However, this pattern is going to continue. So this is actually going to be a discrete graph, okay? However, because this pattern of this discrete is going to continue forever and ever, what we're going to do is make a line just to show the trend. However, when we do our domain and range, so we have our points, our distinct points, and then, but there's a trend. This pattern is going to continue on and on forever. So that is going to be affected in our domain. So our domain is going to equal just the points. So 0, 1, 2, 3, 4, and then we're going to do this dot, dot, dot. Okay, and that dot, dot, dot just means that pattern is going to continue on and on forever. Okay, and then when we talk about the range is going to be, well, what's our first range value? 10, and then 13, and then what is it? 16. So it's like we're adding 3 every time, right? 18. Oh, shoot. No, that's 19. My goodness, joy. 19, and then add 3 to that, and you get 22. You add 3 to that, you get 25. And then that pattern of adding 3 is going to continue on and on forever. So this is how you would express the range for this, just making those 3 dots and showing that it goes on and on forever. So this would be the domain and the range for this particular problem. All right, that's it for this lesson. I'll see you next time for lesson 2.